Hello friends, so in this video I will talk about linear regression, and it's not about how you can implement linear regression using some library, but you can implement this linear regression algorithm from scratch. So you don't need any library, you don't need any package, just you would be using the basic libraries like NumPy, and you are good to go. So you will be using basically stochastic gradient descent. Basically it is an algorithm for optimization of any kind of algorithm like linear regression. So this algorithm, which is a stochastic gradient descent, it's basically used to minimize some kind of function. So function is, let's discuss about. So we will begin with importing some libraries. So this will be NumPy and matplotlib for visualization and NumPy for algebra part. So in NumPy we have the array. So it is one dimensional, two dimensional, or it can be n dimensional array. We will begin with the arrays, and let's import NumPy as np and import matplotlib.pyplot as plt. Now once we have imported these two libraries, what we are going to do now is we have to, let's do it separately. We will be now running this x and y. So as we know, in whenever we have any kind of regression problem, and since it is called linear regression, definitely there will be some line which is explaining the variance of y. Means you are trying to explain y as a function of x and as a linear function of x. So we know that from basic mathematics that y is equal to mx plus c, that is y is equal to some slope times x plus intercept. That is the equation for a straight line. So let's define what we are doing is we are writing one list, and this list is having some elements like 1 1 2 2 2 3 3. So these are x values, and then we are converting this list into an array, NumPy array. Then again we are defining y. For a corresponding x1 there is value 10. The next point x is 1, then y is 10. The next point x is 2, y is 20. Like this we have these values. What we want to do is, let's first import this and then this, and let's insert one more one. Now we will be using matplotlib, which is this one, matplotlib.pyplot as plt. Let's just see how this values are looking like. So we will be using plt.scatter. This is a scatter plot of how the y is changing with x. Let's see. So we have to write %matplotlib inline. Okay, this is for just to visualize this thing inline. So now we have the values. We see that x ranging from 1 to 6. This is the x-axis. 1 2 3 4 5 6. And for corresponding x we have y. So for x is equal to 1, y is equal to 10. X is equal to 2, y is equal to something more than 20. Like this we have x is equal to 6, we have something around 63. X is equal to 6, something around 63. We have number of values like 6 6 6 6 6. For all these 6 we have these values 59 57 62 50. That's why for a given point in x we have different values in y. So this is just a there are definitely some assumptions behind this linear regression, but just for simplistic case, you're just taking random, we are just taking some values, and definitely if you see and show it anybody will say that a line can be passed out through these points. So we can see that there is a line which is something passing like this, all these points. Definitely, so this data can be explained with the linear regression. Maybe data is little bit curvature or maybe it has a lot of variance at when we have x is equal to 6, we have a lot of variance. We will not bother about all those things. Let's consider that we have this data and we want to implement the linear regression in this kind of data. So in the next video, I will explain more theory about this, and we can see that we can see what is cost function and what is the gradient, why this is called a stochastic gradient descent. Basically in the next video I will be explaining. Right now in this video I just told you that how to import the libraries, what is x and what is y, and for a corresponding y, corresponding x, we have a corresponding y, and now we want to fit a line to this data, something like this, diagonal line, something like this we want to fit. And this fitting line, because why it is interesting is because, see, somebody can fit a line something tilted from here till there, someone can fit a line from here to here, and somebody can fit a line from something in between, middle here till there. So a lot of possibilities are there, but what is the important thing and how you choose the best line, that I will be explaining in the next video. Hello, so in the last video we discussed about that we are going to fit a line, a straight line to a data, something like this. So now we are going to discuss little bit more that what is the predicted line and why we are trying to fit a line, and what do you mean by best fit of line. So how do we say that this is the best line? I will try to explain you. So let's we already discussed this data x and y. Now what we are saying is, and this x and y data looks like something like this. I have commented the second line. It is just a scatter plot of x and y. So this is how it looks like. X is along x-axis and y is along y-axis, and this is our data. So if somebody asks you that what you would like to fit in this kind of data, definitely a straight line passing through something like this nearby the origin will be a very good fit. So linear regression is a perfect model for this kind of approach. So once the line is fit, we know that for any value of x, what will be the predicted value of y, because we can extrapolate that line and interpolate as well, because we know the values of 6 for 6, x is equal to 6, we know the values, x is equal to 5 we know, and x is equal to 4 we know, and we see the pattern, it's going like a straight line. So if somebody asks that what is the value of y given x is equal to 5.5, we can definitely extrapolate from here, and we see that it should be something in between like this. So it will be something like 55 or something like that. So this is the benefit of performing the linear regression. Now the question is that which line. So let's assume that we know that, we pretend that we know that what is the best fit, though we do not know. But let's say y is equal to mx plus c. We already know the equation of a straight line is given by y is equal to mx plus c, where m is equal to slope and c is equal to intercept. This is very basic mathematics which everybody should know. Now, and we are defining the predicted line. We are defining the predicted line. How we are defining? For a given x, m is 10 and c is minus 5. Let's say this. Then once we have defined, we will see that predicted values for each value of x, we will get the predicted values of y. So for x is equal to 1, we get 5. X is equal to 2, we get 15. X is equal to 3, we get 25. Like this we get the values. For x is equal to 6, y is equal to 55. These are the predicted values. We defined this line. And the aim of using the stochastic gradient descent is to get these values, m and the c value, because we do not know what is the perfect values for these. We can just estimate by seeing, but that's not the good choice. So that's why we use an algorithm like a stochastic gradient descent to come up with the best values of m and c. But for the sake of purpose of showing you that how this predicted lines and will show up, then I am taking an example. So y predicted is this one. Let's remove this part, and now let's do it once again. So scatter plot of x and y, and just plot a line of x and y predicted. We see this is the predicted line and dots are the actual data. So we fitted this line on the basis of our hit and trial. This is just an hit and trial. We are seeing that the line is passing from the origin. So we chose an intercept something nearby, that is intercept is -5. And we also see from the data that for x is equal to 1, we have 10, x is equal to 2, we have 20. It's something like 10 factor times of x. That's why we chose 10x. And intercept we can choose 0 as well. Let's see what happens when we fit +5 instead of +5. So if we do +5, then we will see that this line will go up. See, now this is again not a good choice. We can see that, and earlier choice was also not good because it was going below. Now let's just fit +2 and then try again. Now it is coming near. Let's try +1. Again it is coming near. Let's try 0.1. It's almost perfect. So we can say this is the predicted equation for that. This is m is 10 and 0.1 is the intercept. So here we have tried hit and trial. This is not possible for the real scenario when we have a very big data, or we cannot do that. So we should come up with some kind of algorithm which automatically finds out these values for you, parameters like slope and intercept. Also, we have taken 10, but let's say if we choose 5, what happens? Let's see. Now see, this line is completely out of the best fit line, which should be, because it is completely out. Our values are going here, but line is predicted line is completely going outside of that range. Let's do it like -5. Let's see what happens. Now it's going more and more that way. Let's do +15. Now it's going there. Let's do L12. It's coming near. So definitely there are two parameters which you have to optimize. One is slope and the second is intercept. I hope it is very clear that these two parameters are required to be found by the stochastic gradient algorithm, so that you get the best fit. And the best fit, I assume that it is something nearby this, but you do not know it is 0.1 or 0.01. You do not know it is 10 or 10.1. So that algorithm will be telling that how accurate we can fit. Let's take, so this is almost perfect, but we have to find it out using all the possible combinations of M and C, slope and intercept, using the stochastic gradient algorithm. Now let's see what is x. X is a vector right now. So if you see, and y is also a vector, if you see the 0th value, this is 10. That means this is the first element of y. If you see the second, this is 10. If you see the third. Hello friends, so in this video I will be talking about the stochastic gradient descent. Basically, what does it mean? In the last videos I've already explained about what is linear regression, what is the best fit of line, and why do we want to use that, and how does that make sense. But in this video I will be talking that how we are using a stochastic gradient descent for the linear regression optimization, though it can be used for other algorithms as well, but we are just now discussing about the stochastic gradient descent, a simple case. In the linear regression, we already discussed that we have two kinds of parameters. One is slope, which is this one, and the other is intercept. So it is y is equal to mx plus c, and we want to find the slope and the intercept values by using the stochastic gradient descent. So let's say we have only, for the simplistic case, let's say we have only one parameter, let's say it is slope. So we already discussed for the cost function for the linear regression is this one in the last video, and this is like actual values minus predicted values of y, square it for each of the data points and add them and divide by the total number of data points, that is total number of rows, total number of observations. Okay, now so let's take, so we know that predicted. Now if you see this cost function, this cost function is basically the error which we want to minimize. And if you see, then this cost function MSE, that is function of all these values. We see n is the data points numbers, that is fixed, so we cannot change that. Now yi is the actual value data points, so that is also fixed because the data is given, that is fixed. But this predicted line is not fixed. Predicted line is keep on changing as we keep on change the parameters, the slope and the intercept. So we can say that cost function MSE here is a function of slope and is also a function of the intercept. Here we are assuming that intercept is, let's say, we are neglecting that intercept is, let's say it is constant. So only now the cost function becomes only a function of single variable, single parameter, that is the slope. And now if you want to plot this, you will see that it is a function of some variable square. We know that is an equation of a parabola. So in the y-axis we are plotting this cost function, and the x-axis we are plotting this parameter, not the y but the parameter, which is the slope. So w is the slope here. Let's say w is a slope. So the cost function is a function of slope and it is quadratic in nature, like it's parabolic. And from here the stochastic gradient descent begins. So we can see that as the parameter w changes, the cost function changes, but we want the minimized value of MSE, minimized value of cost function. How do we get that? We want to get this value, but how do we reach? How do we know that this? Because we do not know that at this point of at this place we have the minimum cost function. We can only know when we plot all these values, but we are not using this 3D geometry and visualizing and then seeing that this at this point and that we are getting the lowest cost function. What we will do is we will randomly initialize some parameter, this slope. Let's say we started from this algorithm, started from this. What the algorithm will do is at this point it will find a slope of cost function with respect to parameter w. So it is like derivative of j with respect to w. It is here derivative of cost function with respect to the slope. So if you see on the right hand side, means from this center on the right hand side, you see the tangent will be always be, slope will always be positive. On the left side the slope will be negative. So we started from here. Let's say this is the initial value. Now we want to reach here. How we will reach there? So we will find the slope here. We know the slope is negative. From here we can either go up or we can either go down. But if we use this formula m nu, so we have this m nu is this point. What we are doing is we are subtracting. Learning rate is actually how fast you want to move on this curve, how fast you want to reach the bottom point. There are also pros and cons, that if you choose very high and if you choose very low, there are pros and cons that I will explain later in other videos. This is just how fast you are moving across the curve. So m grad is actually the slope. That is the slope of cost function with respect to m, that is the slope. So this m grad is the slope, and if it is negative, then this m nu becomes negative and then negative again, that becomes positive. That means this m will be, the new m will be more than this m nu. So if m grad, that means the slope is positive, then this new, this one will be, if m grad is negative, then negative becomes positive. So m nu will be positive. So if we are here, slope is negative, due to which the new m value will be more than the initial value, old value, and then new value will be more. So if we are here, we will go towards this, because we are moving, because as we move towards the right axis, if we move from left to right, new values will be more of slope. As we go from right to left, mu will decrease. That means w will decrease. So if we are on the right hand side, we get the slope as positive, and negative and positive becomes negative. So new m will be little less than the initial value. So if we start from here, in the second iteration we will come here. In the third iteration we will come here. In the fourth iteration we will come here, because we are decreasing the w values, we are decreasing the slope values. But if we start from here, again this formula, we have the slope negative, so negative, negative, positive. Learning rate is always positive, so only m grade is positive or negative. So if this is positive, then this becomes this minus something. If this is negative, then this becomes this minus something. So you have to take it, if you are here, then m grade is negative, 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 positive, then m new will be more than this one initial value. So if we start from here, we will go towards here. We'll start from here, we will go toward here. And in this way, stochastic gradient descent, we can come near to this value. But I was saying that why, if learning rate is very high, what will happen? If learning rate is very high, let's say m new is some value which is here. Now you have m grad which is positive. So minus and plus becomes minus. So that is sure that you have to go towards left, because this will decrease m. But how much it will decrease, that will depend on the learning rate. If you Hello friends, so in the last video we already discussed about what is a stochastic gradient descent and how you can use for linear regression to find the best parameters for the slope and the intercept for the linear regression. But you can use in general for stochastic gradient descent for optimization, for the minimization of any algorithm. We already discussed what is cost function. So cost function is for the linear regression, this is this one, and it is a function of yi predicted, and the predicted y value is a function of slope and intercept. So it is a function of two variables, slope and intercept. So if you want to find the cost function at a given point of time, say this is the cost function and this is the parameter, and we randomly choose any value for the parameters. Let's say we are at this point. Once we know that the random value of slope and the intercept, we can put the values here in the y hat, y prediction, because we know the y prediction is, we start from here, y predicted is equal to slope times x plus c. So x are the x values and m is the slope which we randomly choose an initial value, and the c is the intercept. So this is how the initial random predicted values of y we get, and we already know the actual values of y. We just subtract them, actual values minus predicted, square them, and add all the data points, errors, and divide by the number of observations, number of data points. This is how you get at the first iteration you get the cost function value. But that we want to minimize as we move ahead in the iterations. First iteration, second iteration, that is also called epochs. So now let's go to the coding part. So we are defining a function which will with the name LR. We are feeding in x and y. That is the data. X and y is the data. Given x, what are the value of y? We feed in the random value of slope m and random value of c. We give some learning rate that you can choose how fast the algorithm should learn. That shouldn't be very high, shouldn't be very low. That depends on what is high, what is low, and in your case and the data. So you have to try it out. So epoch, number of times you want to run this iteration, that is the stochastic gradient descent, how many times you want to run it before it reaches at the minimum. So if you do not run it sufficiently, maybe it end up here, and maybe if you run it many number of times, it may not end up here, it may go somewhere else. So you have to optimize that. N is the number of observation that you can just float length of y, and for I in range of epoch, that means we are saying that for each iteration, so it is looping over the iterations. So the first iteration, second iteration, what will happen? So first iteration, we want the y predicted, y actual is y, Y predicted is y new, m new, x plus c, but that is mx plus c. Once we know the y predicted, we can find the cost function. Cost function is this one, y minus y new, and for each data point we square them, add them, and divide by the number of observations. Then we get the gradient for c, then we get the gradient of m. We already know the formula for the gradient of c and m here. Y minus y predicted divided by n and 2. That is just the derivative of this cost function with respect to slope and intercept. This is for slope and this is for intercept. You get the grad for m and c. Once you get the grad, you can find the new m by old m minus learning rate times the gradient. Similarly for c, old that means the c new, that keeps on updating. So this is the initial value we feed in, and that just keeps on iterating as we iterate it for the second epoch, third epoch, and so on. The m new keeps on changing, and as m new and c new changes, the line also keeps on changing. Mx plus c, so m new changes, c new changes, the line will change. And we want to visualize, we just added these three lines, and we added this pause just to visualize that how, as the epoch changes, how this looks like. So I will show you that how it looks like. I will restart it because I have somewhere written inline. So let's start from here. I will remove this because I want to show you the dynamic visualization in the real time, how this gradient descent is working in the real time. So let's take x and y, and we know x, y, and just run this function. What is it returning is m, c, and cost. Okay. That is the after all the iterations, it will return the updated values. So we will just run x is equal to x, y is equal to y, which we will just define there, and m new 0, that is the initial values. We can choose anything. Learning rate, we just chose 0.04, and epoch just for 10 observations, 10 iterations. We want to run this stochastic gradient descent, and we will look in the dynamic visualization how the line is trying to move towards the best fit for the data we have. So it's quite cool. Let's see. As you can see, it is trying to come towards the data cloud.